Hello students, in this video we are going to solve previous year JEE Mains and Advanced Chemistry questions related to the topic Haloalkanes and Haloarenes. I will solve each and every questions with explanation so that we can revise our chemistry concept. So let's start this video. The first question is the decreasing order of reactivity of the following organic molecules towards silver nitrate solution. So we should know that whenever we see the reaction of silver nitrate with halides, then it leads to the formation of carbocation and silver salt as silver halide precipitate out. Why is it so? Because silver ions has strong affinity towards halides. Therefore, it leads to the formation of the carbocation. So the rate of reaction will be directly proportional to the stability of the carbocation. And we know that tertiary carbocation is more stable than secondary carbocation, and secondary is more stable than primary. But here all carbocation are secondary carbocation. So we have to see which one is more stable. So if you make the carbocation of this, it will be like this, and this carbocation positive charge delocalized due to the conjugation with the pi electrons. So this carbocation is stable. Now let's check this one. This is also stable because of the positive mesomeric effect of the methoxy group. So lone pair is in conjugation with this pi, and therefore this is stabilizing more effectively as compared to the A. So the most stable carbocation will be B and then A. Now let's look at this C. C will give secondary carbocation, and the secondary carbocation will be least stable as compared to the to A and B, because resonance stabilization dominates over plus I effect, and here you have only plus I effect of the methyl group. Therefore B is more stable and A is less stable than B, and A is more stable than C, and D is the least stable due to the presence of nitro group which has minus I effect. Hence the order of reactivity will be B, A, after that C and D, and if you see, this is matching to the option D. So the correct answer is D. Now the next question is, which of the following compounds will form the precipitate with aqueous AgNO3 solution most readily? So it means, as we discuss here, the formation of precipitate depends on the stability of carbocation. So we have to see that which carbocation is forming faster will give the precipitate faster, and that should be more stable carbocation. So these are the options. In option A, if you break this bond and put the positive charge, this carbocation is not stable. So for sure it will not give precipitate silver bromide. This is the precipitate which we are talking. So this precipitate will not form faster. Now let's see the option B. In option B, this carbocation positive charge will stabilize due to the presence of lone pair in conjugation with this empty p orbital of this carbocation, and it will give this stable carbocation. Now let's see option C. In option C is also this nitrogen lone pair is in conjugation with this positive charge, hence it stabilizes this carbocation also. And in option D, it is the same reason, that positive charge stabilized by the lone pair of the nitrogen atom. So you can see that in B, C and D, in all the cases carbocation is getting stabilized, but now we have to find which one is the most stable carbocation. If you know that nitrogen and oxygen has more electronegativity than nitrogen, therefore tendency to give the lone pair for nitrogen will be more than oxygen. So this is the tendency of nitrogen to share its lone pair of electrons will be more as compared to the oxygen, and hence we can rule out that, hence we can see that carbocation B will be less stable than C and D. Now we have to choose from C and D. If you see that nitrogen of this compound lone pair is also in conjugation with the phenyl ring or benzene ring, it is in conjugation with the benzene ring, hence it is less available to stabilize the carbocation. But in case of D, the lone pair is not in conjugation with this ring and completely available for stabilizing the positive charge. Hence D will have more stable carbocation, therefore it will give more readily precipitate with this silver nitrate solution as silver bromide. So the correct answer is D. Now, among the following compounds, which one has the shortest carbon-chlorine bond? So shortest carbon-chlorine bond, we have to look which compound has partial double bond character. If you see this compound, in this case you have only single bond character, single bond. In this case also, the lone pair of this halogen is not in conjugation with this pi. Therefore it is also has single bond character. Here is the same, but in this case the lone pair of the halogen are in conjugation with this pi bond. Hence here carbon and chlorine has partial double bond character. So therefore the bond length in option D will be shorter. So the correct answer is D. Now moving to the fourth question, the mechanism of SN1 reaction is given as. So let's understand this scheme. This is the alkyl halide, and alkyl halide break down to give carbocation and halides as an ion pair. Then after that, protic solvents play an important role to separate these anions, and after that nucleophile attack to give the compounds. So in SN1 reaction, we know that carbocation is forming without attack of nucleophile. So you don't need strong nucleophile, and this carbocation has planar geometry. Therefore the nucleophile can attack from the front and from the back to give the racemization of the compounds. Now let's see what are the options. So the question is saying that the reaction is favored by weak nucleophiles. So we can say yes, this is correct. Carbocation would be easily formed if the substituents are bulky. Yes, because tertiary carbocation are more stable than secondary and secondary is more stable than primary. The reaction is accompanied by racemization. This is yes, because carbocation has planar geometry and therefore nucleophile can attack from back and front to give inversion and retention of the configuration, which leads to the racemization. The reaction is favored by non-polar solvent, so this is not true because you need polar protic solvent to separate the ion pair. So we have to which observations are correct. So first, second, and third observations are correct. So therefore, option C is the correct answer. Now let's move to the question fifth, the major product of the following reactions. So we have to understand that what is this reaction? This is the alkyl iodide reacting with tertiary butanol under high temperature. So tertiary butanol is not nucleophilic because it is tertiary butyl is bulky. Therefore, this reaction is not going to occur through nucleophilic substitution. So option D we can rule out. Now we have to see other options, and after looking these options, it is indicating that the reaction is following either E1 or E2 elimination pathway. Since we don't see base in this reaction, therefore this cannot be E2 reaction. It means the reaction is following the E1 mechanism, and E1 mechanism we know that first step is the formation of carbocation by the breaking of this carbon halogen bond, and after that we have to see that if there is a possibility of rearrangement to give more stable carbocation. So we can see that here there is a possibility that this hydride can transfer to this carbocation, and this is called 1,2 hydride shift, and to give the more stable carbocation. This is the more stable carbocation, this is tertiary carbocation, this was the secondary carbocation, now you have tertiary carbocation, and this tertiary carbocation has two beta hydrogen, one is here, and now we have to see which beta hydrogen will go away. So if you remove this beta hydrogen, then you get this product, which is least substituted double bond, and this is according to the Hofmann rule. And if you remove this beta hydrogen, then you get more substituted alkene according to Saytzeff rule. Now we have to understand which rule we have to apply here. Since Hofmann rule is applied when you have more acidic beta hydrogens. For example, if you see fluoro or N plus R3 group, in that case, you have to apply Hofmann rule. Otherwise, you have to apply the Saytzeff rule. Therefore, formation of this product according to Saytzeff rule. Out of this, you can see the correct answer is C, not B. I hope this is clear to you. Now let's move to the question number 6. Which of the following compounds will show retention in configuration on nucleophilic substitution by hydroxide ions? So first option, in first case, you can see that this is the chiral center, which because it is attached to 4 different groups: methyl, this is another alkyl hydrogen, and bromide. So in this case, for sure, you will get the either inversion of configuration or racemization. If it follows the SN1, then racemization, or if it follows the SN2, then you will get retention of the configuration. This is also chiral center, and in this case also, this is benzyl halides, and in benzyl halides, it can favor SN1 or SN2 both, depending upon the conditions given for the reaction. So here, if you will have the same problem, that you will not get the only retention in the configuration. Now let's see what other options are there. This is not chiral center, this is non-chiral. So if you attack here, nucleophile attacks here, so you will still get this non-chiral alcohol. So there is no discussion about retention or inversion of configuration because the reactant itself is a non-chiral. Now let's see option D. In option D, we can see that this carbon is chiral, and what is the possibility here that these halides break down to give this carbocation, and then through rearrangement it gives more stable carbocation, tertiary carbocation, and after that this hydroxide nucleophile attacks to give this product. Now in this product, let's make it bond. If you see these two carbon are same, this is methyl, same methyl groups, hence it is non-chiral center, non-chiral. So if you see that the compound reactant was chiral, but product is a chiral. So in this case, we can say that retention of configuration take place. So the correct answer will be D. For me, this question is quite unclear, but we can explain only this way that this was the chiral center, and then you are getting non-chiral center, and hence the option D will be the correct answer. Now let's move to the question number 7. So the major product obtained from E2 elimination of 3-bromo-2-fluoropentene is. So first let's draw the structure 3-bromo-2-fluoropentene. 1 2 3 1 2 3 4 5. So 2 fluoro, so fluoro, let's put here 2 fluoro and then bromo. Okay, so this is the structure of this given compound, and it is saying that undergoes E2 elimination. So what will be the major product? Now it is very interesting here, because E2 elimination involves removal of beta hydrogen, beta hydrogen by base, and simultaneously halides goes away. Now if you see, we have one this beta hydrogen, another this beta hydrogen, so we have two beta hydrogen. If you remove this beta hydrogen, then double bond will come. If you remove this beta hydrogen, then double bond will come. You are removing this, and then you have this. So if you see, where, so it is matching to which options? If you, so this is matching to option C, right? It is matching to option C. But if you remove this beta hydrogen, then what will you get? Then you will get, then you will have this product, and it is matching to which one? It is matching to B. So answer could be C or B. Now we have to understand which is major product. So as I discussed in the previous questions, that more acidic hydrogen, this is the more acidic hydrogen, due to the presence of this fluorine, which has very strong electronegativity, makes this hydrogen acidic as compared to this hydrogen. Therefore, this hydrogen present at the fluorine carbon will remove first and give the product according to the Hofmann rule. Hence, B will be the major product. So the correct answer is B. So moving to the question number 8, consider the reaction sequence given below. So the first reaction, this one is the example of SN1 reaction, and the rate is depending on the reactant concentrations, not on the concentration of the base. And the second one is, uh, after looking this formula, we can say that rate of the reaction is depending on the concentration of reactant and base. Therefore, this reaction is following E2 pathway. Now, which of the following statement is true? Changing the base from hydroxide to alkoxide will have no effects on reaction 2. So this is not true. It is a false statement, because if you change from hydroxide to alkoxide, then this elimination of the proton will be faster, and therefore it will have for sure the effects on reaction 2. Now changing the concentration of base will have no effects on reaction 1. So if you see, the rate of the reaction depending on the concentration of reactants, not on the base. Therefore, the statement B is correct. Let's see what is option C. Doubling the concentration of base will double the rate of both the reactions. So actually, doubling the concentration of base will double the rate of the reaction for only reaction 2, because in this case you can see that it depends on the concentration, but not for the reaction 1. Therefore, statement 3, this is false. Now changing the concentration of base will have no effects on reaction 2. This is also false, because as we see that if you change the concentration of base, will have effects on the reaction 2. So this is also false statement. So the correct answer is B. This is the correct answer. Now moving to the reaction number 9, the decreasing order of reactivity towards dehydrohalogenation following even mechanism for the following compounds. So we know that even reaction follows carbocation pathway, carbocation. Therefore, rate of even reaction directly proportional to the stability of carbocation. So we have to see which carbocation is more stable. So let's start from here. So this will give you primary carbocation. And if you see here in case of B, so you will have after breaking this bond, the positive charge will come here, and then this hydride shift will bring the positive charge at allylic position, and these allylic carbocations are more stable due to the conjugation of these pi electrons, and allylic carbocations are more stable than secondary carbocation. Okay, so now let's see the option C. This will give secondary carbocation, and this will directly give you allylic carbocation. And allylic carbocation is more stable than secondary carbocation. So among B and D, the most stable carbocation will be given by D. So in option A, there is only one option in which D is at the highest. Okay, so let's see which one the least one. So A will be the least stable carbocation, and which is in the end. Therefore, the correct answer is A. And you can also see that after D, the stability of the carbocation B is more as compared to secondary carbocation. So without any doubt, the correct answer is A. Now moving to the next question, consider the following reactions. So this is the dehydration reaction. This is elimination reactions because you have alcoholic KOH, strong base, and the reaction third is also elimination reactions. And fourth, actually, in fourth, the correct formula is this is something is missing here actually. So I want to write the correct one, CH3 to CHOH. So this is the correct structure of this compound. Okay, so we have to see which of the reactions will not produce Saytzeff product. So Saytzeff product is that product which gives more substituted, more. Okay, so let me write this structure, proper structure of all these molecules. Okay, so I have wrote the structure. So in the first case, if you see this hydroxy will undergoes removal of water and give the carbocation, and this carbocation will get stabilized to the tertiary carbocation, and after that this proton will go away and it will give the more substituted alkene. And in case of reaction 2, if you see alcoholic KOH is a strong base, so therefore it will abstract this beta proton. So after abstraction of this beta proton, you will have more substituted alkene. This will be the product, and this is according to the Saytzeff. So this is the more substituted alkene. Now let's look at the option 3. In option 3, you have two beta hydrogen. One is this, and another is from this methyl. But since this tertiary oxide is very hindered base, this tertiary oxide is a hindered base, due to which this will not be able to abstract this proton. Not possible because of the steric crowding here, steric crowding and bulky base. Therefore it will prefer to abstract the proton from this place and give the less substituted alkene, and this is Hofmann product. And now look at the last option, fourth. In the fourth case, it will undergoes dehydration of the water on heating, if you remember the aldol condensation reaction. So this is beta hydroxy, and beta hydroxy undergoes elimination of water molecules and gives alpha beta unsaturated carbonyl compounds, and this is also more substituted one, and this is also follow the Saytzeff according to the Saytzeff rule. Hence the correct answer will be 3. Only 3 will give Hofmann product and not Saytzeff product. Question 11, the major product of the following reaction. Okay, so this is dihalide, 1,2-dihalide. Whenever you see 1,2-dihalide reaction with alcoholic KOH and after that soda amide in liquid ammonia, then it leads to the formation of alkynes, triple bonds will come. And so if you see in the given option, the correct answer will be D. And the mechanism is as follows. For abstracting this proton, you need a very strong base, and soda amide is very strong base. So therefore it will abstract this proton, and removal of the HBr will give you this triple bond. Now moving to the next question, which hydrogen in compound E is easily replaceable during bromination reaction in presence of light? So bromination reaction in presence of light is the example of radical reaction. So this bromide radical will form. So we have to see which hydrogen removal will give the stable radical, and we know that allylic radical is more stable than vinylic radical due to this resonance, and this radical delocalized to other position. Therefore hydrogen at C will easily replaced. So the correct answer is C. Now moving to the question number 13, the major product of the following reaction. This reaction is very difficult and very interesting, and believe me, you have to think in every aspects. You need very great knowledge of SN1, SN2, E1, E2 reactions. So we will think in all the possible ways. So imagine that sodium methoxide is attacking below the plane, then it leads to the formation of this product and through SN2 mechanism, and this is matching to D. Okay, we can also think that this reaction can follow SN1 pathway. So if we follow SN1 pathway, then first it will form the carbocation. After that, stabilization of the carbocation by migration of this methyl group, and then removal of this proton to give alkene. So this is matching to option C. Now let's think another possibility, that this is a strong base. Sodium methoxide is a strong base, and it is abstracting this proton from the beta position, and this is anti-periplanar. And after abstracting this proton, at the same time, removal of the halogen gives alkene through E2 mechanism. Now, option A we can easily rule out. So this product cannot be have retention of the configuration. Okay, inversion is possible through SN2 mechanism. Okay, now let's think about which possibility we should rule out. Since this is very strong base and this is secondary carbocation, so you can think about SN1, but due to strong base, we can rule out SN1 pathway because of the presence of the strong base. Now two possibility left, E2 mechanism or SN2. For SN2, you need nucleophile should approach to the halides carbon. But if you see, this is 4 substituted carbon, and here it is secondary carbon. Therefore, this presence of the big methyl group is hindered the approach of the nucleophile, and hence it rules out the possibility of this SN2 product. Now what is left? E2, elimination E2. Yeah, this is the only options left. And why? Because this hydrogen, there are two hydrogen, one is anti-periplanar to this bromo, and removal of this hydrogen through this strong base lead to the formation of this alkene. So the correct answer is B. So again, I am saying why it is following E2 pathway, because of the strong base and steric hindrance at the beta position prevent the SN2 pathway. So that's why the correct answer is B. Okay, so the next question is, which of the following will most readily give the dehydrohalogenation product? So dehydrohalogenation product are possible in E1, E2 and E1CB reactions. So but the given reactions, if you see the given substrates have vinylic beta proton and vinylic beta hydrogen. Therefore, vinylic, if you remove the vinylic beta hydrogens, then it will give the carbanion. So we can rule out E1 and E2 possibility. So all these substrates will follow E1CB mechanism, and in that case, carbanion will be intermediate. Now we have to see that which will give more stable carbanion. So after removal of this, negative charge will come here, and this negative charge will delocalize over this phenyl ring. Can easily delocalize over this phenyl ring to stabilize this negative charge. In this case also, negative charge can stabilize through the sp2 negativity of this carbon, and through the resonance also. If you see here, this removal of this proton will give negative charge, and this will only stabilize through the sp2. So there is a resonance stabilization, here is also resonance stabilization, but in this case only stabilization through the electronegativity. And now what is going to happen here? In this case, you will have, after removal of this proton, you will get benzene, and benzene is benzene. It is highly reactive, highly reactive. So out of this, which one is giving the most stable carbanion will react faster? So the option A is the correct one, because in this case carbanion is stabilized through this phenyl ring as well as conjugation with this double bond. But in this case, stabilization is only less number of resonating structure as compared to A. So in A is more stabilization than B. Hence the correct answer is A. Now moving to the question number 15. Which of the following reagent is not suitable for the elimination reaction? First reagent is sodium iodide. If you remember that reaction of alkyl halide with sodium iodide leads to the replacement of the halides by iodide, and this is known as Finkelstein reaction. And the rest of the cases, in remaining cases, this is the base. This is ethoxide base, hydroxide base, and this is also hydroxide base, and it can easily remove this beta hydrogen, leads to the formation of alkene, and hence the correct answer will be A. So A, sodium iodide, will not lead to the elimination of the reaction. Now moving to the question number 16. The synthesis of alkyl fluorides is best accomplished by Finkelstein reaction? No, as we have already seen, this Finkelstein reaction involves the reaction of alkyl halides with sodium iodide. Swarts reactions, yes. In Swarts reactions, we use the reaction of alkyl halides with fluoride, source of the fluoride, such as these, or antimony fluoride to give alkyl fluoride. Free radical chlorination, no. Sandmeyer reaction, no. Sandmeyer reactions involve the diazonium salt formation, and then attack of the nucleophile. So this one no, this one no. So the correct answer is B. Now 17. In SN2 reaction, the correct order of reactivity of the following compounds. So SN2 reactions follow. Primary is alkyl halides is more reactive than secondary and then tertiary. So we have to see the correct option. So if you see, this is the CS3 should be first. So in which cases here the CS3 is first position, CS3 methyl is first. So out of these two we have to choose, and then this is the primary, and here is the secondary, and then after that secondary, and then tertiary. So the correct answer will be B. Now moving to the next. For the compounds, this the correct order of increasing carbon halogen bond length. So carbon halogen bond length. So if you see this down the group, from fluorine to iodo, size of the atom increase. Therefore, the size increase in the size, the bond length is also increasing. So carbon iodide bond length will be more than carbon bromide, and so on. So the correct answer will be first A. A will be the correct answer. Now the order of reactivity of given haloalkanes towards nucleophile is order of reactivity. So this we can explain in two ways. First, by using the concept of good leaving group, leaving group. So we should know which is the good leaving group. Iodide is better leaving group than bromide, and bromide is better than chloride, and chloride is better than fluoride. Because of the big size of the iodide, the negative charge gets dispersed. Okay, so the correct order, so therefore the reactivity towards nucleophile will follow this order. And we can also explain through the bond energy. Carbon iodide will have lower bond energy as compared to carbon bromide, and carbon chloride, and then carbon fluorine, because of the small size of this bond, this will be more difficult to break. Therefore bond energy is increasing in this order, and therefore reactivity is also decreasing in this order. Okay, now moving to the question number 20. This question is very important, so let me remove this all those things. Okay, this question 20 question reaction is very important. So it is asking potassium iodide in acetone undergoes SN2 reaction with each of these molecules PQR and S. The rate of the reactions vary as. So what will be the rate of the reaction? So we know that potassium iodide in acetone follow SN2 pathway. Following the SN2 pathway, so now we know that primary alkyl halides reacts faster than secondary alkyl halides, and then tertiary. So here we can see that P is the primary. Sorry, this is 0, it's not even primary. So this should react faster as compared to Q, because this is secondary, and this is allylic. This one is allylic. But here is very interesting molecule, this which is S. This is alpha haloketone. We should understand the reactivity of alpha haloketones. If you see this alpha haloketones, then without thinking anything, understand that this has very high reactivity as compared to primary. Alpha haloketones has very high reactivity. Haloketone has high reactivity as compared to primary alkyl halide. We should understand these things very clearly. Why is it so? There are two reasons. First, this carbonyl group is electron withdrawing group, and therefore this creates the partial positive charge at the alpha carbon. So partial positive charge positive at alpha carbon. So increase the electrophilicity of this. And second reason, in SN2 mechanism, transition state has negative charge, and carbonyl group is electron withdrawing group. Therefore, stabilize the negative charge. Therefore, reactivity of S will be higher. And then now which one will come second, P or R? Look, it is very interesting. If you have primary alkyl halides, then for sure allylic will be more reactive. Allylic halide will be more reactive, but you have 0 directly connected to this, so that's why P is more reactive than allylic halides. And secondary is of course coming at the end. So which is the correct options? So the correct option is B. Luckily in this case only one option has in which case they are showing the S has higher reactivity. So once you find this, then you are all set. But imagine if you have one more options with the S, then it could be a problematic. And we have to be very careful between primary alkyl halides and allylic halides. Allylic halides are more reactive than primary alkyl halides because of the sp2 nature of this part stabilize the negative charge during the transition state of the SN2 reaction. Okay, now moving forward, the reagents for the following conversion. So we have already seen before. So this is the vinyl dihalide. So alcoholic KOH, yes, alcoholic KOH can remove one of the halides, but after that, to get this one you need soda amide. So this one, alcoholic KOH followed by soda amide. Yes, this is the correct answer. Aqueous KOH followed by soda amide. No, because aqueous KOH is a strong OH, is a strong nucleophile, so it will lead to the substitution reaction. Substitution rather elimination. So therefore this is not the correct answer. What is the fifth? Zinc assay. Zinc in. No, this is reducing agent. Okay, now moving to question 22. What would be the product formed when 1 bromo 3 chlorocyclobutane reacts with the 2 equivalents of metallic sodium in ether? So we should know first to make this kind of species. So let's draw the structure of this. Okay, so let's say this is bromo 1 3, this is chloro. So first bromo will cleave to form sodium, and it will have partial negative charge. If you remember, this is the example Wurtz react. First it will remove the bromide, and then this carbon ion undergoes nucleophilic attack, intramolecular nucleophilic attack, and gives this kind of product. So correct answer is D. Identify the set of the reagents, reaction condition X and Y in the following sets of reactions. So look, first this is the alkyl halide, and then X giving the product, and after that this. So for sure this product having double bond. To get this double bond, and we need strong base, not nucleophile. We need the base to create the double bond. So let's look the option 1. A dilute aqueous sodium hydroxide. Sodium aqueous sodium hydroxide. So it will be a nucleophilic. So it will lead to the substitution. It will favor the substitution, not elimination. Let's look the option B. Concentrated alcoholic NaOH. Yes, alcoholic NaOH will give this kind of base, and this is the strong base, with low nucleophile favors elimination over substitution. And now let's look the B, HBr acetic acid. Yes, this looks to me correct answer. Let's look what is written further. Dilute aqueous NaOH, no, this is no. And then alcoholic NaOH, okay, the first is correct. This first part is correct, but what about the second part? Okay, in the second part they are giving the bromine. So if you have this product and if you react with the bromine, then it will lead to the bromination at both the double bond, and it will give you this dihalides. So therefore option D is incorrect. So option B is the correct answer. Now a solution of 2-chloro-2-phenylethane in toluene racemized slowly in the presence of a small amount of antimony pentafluoride due to the formation of, okay, so if you see that 2-chloro-2-phenylethane, this is benzylic halide. So so what will be the intermediate? So for sure this will break down and it will lead to the formation of the carbocation, and carbocation, in the case of carbocation, has planar geometry, and therefore it will attack by both sides and leads to the racemization. So the reaction follow the carbocation intermediate. So correct answer is D. Now 25. So this is Grignard reagent. Reaction with the D2O produces. So Grignard reagent easily get proton from the acidic medium. So what will be the product? CH3 3 Mg. So Mg will break down and hydrogen, it gives the hydrocarbons. So since we have deuterium, so it will catch the deuterium. So this should be the correct answer. Let's look other options. CH3 COD, no. This no. This cannot be answer. Other deuterium, no, it will not go to other places, no. So the correct answer is A. Okay, now let's move forward. Reaction number 26. Isobutyl magnesium bromide with diethyl ether in ethyl alcohol. So again it will take the proton. So isobutyl will take the proton to give the hydrocarbon, and ethyl alcohol will goes to the magnesium side. So let's check. This is OH, no, this is not the correct answer. So B, in case of B, yeah, this is the correct answer, because you can see that this is producing the hydrocarbon, and ethyl alcohol is going to the magnesium. Alkene, this is no, and this first part is correct. This is not the correct answer, because this anion part you have to show in the bracket. So this is not the correct answer. The correct answer is only B. Now the chief reaction product of reaction between N-butane and bromine at 130 degrees Celsius. So N-butane and bromine. So bromine will decompose to give Br radical. So, and the Br radical, and the secondary radical is more stable. Radical is more stable than the primary radical. Therefore the product will be B, not this, and in this case this dibromination is taking place, not this one, and the same, not this one. So this will lead to the monobromination, and correct answer is B. Okay, now moving to question number 28. 1-chloroputane on reaction with alcoholic potash gives. So alcoholic potassium, it will lead to the formation of butene through elimination reaction. So this will lead to the formation of 1-butene, because this CH2 alcoholic C2H5 hydroxide, this is a strong base and weak nucleophile. But in case of aqueous KOH, in this case you will get alcohol by the substitution of this halogens. But here the reaction is following A2 mechanism. Question number 29. This question is very important. So HBr addition to 2-pentyne. So let's draw the structure of 2-pentyne. Okay, so this is the structure of 2-pentyne on reaction with HBr. So there is a possibility that the proton can go at this or at this. So CH3, one is this, and second is, okay, so 1 and 2 are two different structural isomers. And now if you see this around this double bond, these substituents and these substituents are different, so they will show E and Z geometrical isomerisms, and similarly here it will show you geometrical isomerism E and Z. So therefore there are four geometrical isomers and two structural isomers. So two structural isomers and four geometrical isomers. So configurational isomers, we should know that configurational isomers is into two categories. One is geometrical, another is optical. So there is no chiral center. So So therefore, there is optical isomerism is not possible. Only geometrical isomer is possible because double bond that carbon have different substituents. So the correct answer is B. Okay, now question number 30. N-pentyne bromide on treatment with ethanolic potassium hydroxide products produces. So you can see that ethanolic potassium hydroxide and propyl bromide. So here is the again it will lead to the elimination propene through E2 reaction. So the correct answer is D1. The reaction condition leads to the best yield of C2H5 chloride. Okay, so in the first reaction, C2H6 reacted with excess of C2H6 reacted with chlorine. So you will have H5 chloride. In this case, also dark room temperature, you will not get the product. And in this case, chlorine is in excess, so you can have monochlorinated, and you can also get dichlorinated product because chlorine is in excess amount. So you will have more products. And in this case, you will like this is also will give you this product. But the question saying gives the best yield of C2H5 chloride. So in these two cases, we can easily rule out. Now we have to choose out of this A and D. So in this case of A, you have reactant, it is in excess amount. So this excess amount of reactant will avoid the overchlorination, and then you will have more amount of the product. But in this case, you can have mono and dichlorination also. Therefore, the best yield of desired product will be in case of A. Hence, the correct answer is A. Among the following compounds, the most acidic is para-nitrophenol, para-hydroxybenzoic acid, ortho-hydroxybenzoic acid, para-toluic acid. So let's draw their structure first. Okay, so you can see that without any doubts, we know that carboxylic acids are more acidic than phenol. So we have to choose the answer from B, C, and D. In case of B, the hydroxy is at para position, and this hydroxy have plus mesomeric effects and hence increase the electron density on this carboxylic group and decrease the acidity. In case of ortho-hydroxy is the same, but after removal of this proton, the negative charge carboxylate is stabilized through the hydrogen bonding, and hence this becomes stronger acid as compared to para-hydroxybenzoic acid. Now in coming to the toluic acid, in this case also methyl has plus I effects and hence increase the electron density over this carboxylic group. Therefore, we can clearly say that the most acidic compound is ortho-hydroxybenzoic acids. But suppose if we have to arrange them in decreasing order of their acidity, then C will be more stronger acid. After that, D, toluic acid, because in toluic acid only inductive effects is there, which is increasing the electron density and which is poor as compared to mesomeric effect. And then para-hydroxybenzoic acid, and the least acidic is a para-nitrophenol. So ortho-hydroxybenzoic acid is the strongest acid, then para-toluic acid, and after that para-hydroxy, and then para-nitrophenol. The number of stereoisomers obtained by bromination of trans-2-butene is, so how many stereoisomers we will get on bromination of trans-2-butene? This question is very, very important. So this is the structure of trans-2-butene. We should remember that bromination gives anti-product, anti-addition. Bromination is a anti-addition, and therefore it leads to the formation of meso compound, optically inactive compound, and hence only one stereoisomer will form. So the correct answer is A. Here I would like to take your time to explain you something more interesting things. The best way to remember that whether you will get meso compound or racemic mixture, I use this analogy, mathematical analogy. For example, if you have trans alkene and this addition reaction on this double bond is anti, let's say it is trans. So I use this mathematical analogy, trans geometry minus trans addition gives 0. 0 means no optical rotation, optical rotation is 0. And which compound has optical rotation 0? Meso compound. But now imagine you have trans geometry and the reaction is with osmium tetraoxide, which is syn. Let's call syn cis. So in this case, I use my mathematical analogy, trans minus cis addition, trans geometry minus cis addition gives non-zero. Hence, you will get racemic mixture. So here you will have dihydroxylation, syn dihydroxylation, but it will be racemic mixture plus minus. But if you have cis geometry, in this case, cis addition will lead to the formation of meso compound. I hope it is clear to you. Let's move forward. Question number 34. Okay, you can see that this is alkyl chloride and secondary 1, 2, 3 tertiary halide. What is the question? So the question is, this compound on hydrolysis in aqueous acetone gives what? So we should understand that this reaction will follow SN1 pathway. So you will get tertiary carbocation. Okay, so let's make the tertiary carbocation from this how it will look. This is tertiary carbocation, and this carbocation can get further stabilized because this this hydrogen can go 1 2 shift to give the carbocation here. Okay, now there is another possibility that this methyl can go here and positive charge comes here. So if positive charge comes here and so one is intermediate, this possible, and second intermediate is, but this carbocation is unstable due to electron withdrawing nature of this nitro group. Hence, the more stable carbocation, this is the more stable carbocation, benzylic carbocation. This is the most stable carbocation due to the positive mesomeric effects of this methoxy group. It stabilizes the positive charge here. So now we can see that there is a possibility of formation of product 2. This product 3 will not form. This product hydroxy will not come at this position because it is unstable. And what about 1? In first case, this is the substitution is taking place directly by the removal of the chloro. So this is also possible, but this one is not possible. So let's see, mixture of 1 and 2. Yes, it is possible. Mixture of 1 and 3, no. Only 3, no. Only 1, no. So we can say that correct answer is A, mixture 1 and 2, because 3 cannot form due to the unstable or carbocation by electron withdrawing group present on this benching ring. Now moving to the next question, which of the following compounds exhibits stereoisomerism? 2-methyl butene, 3-methyl butane, 3-methyl butanoic acid, 2-methyl butanoic acid. So we have to draw the structure of each compound. Okay, so these are the structures of given options. So if you see 2-methyl butene, there is no geometrical isomers because the substituents at this carbon are same hydrogens. So it will not show no geometrical isomerisms. If you see here, this carbon is not chiral because it has same methyl group. Now let's move forward. In case of 3-methyl butanoic acid, this you have same substituents on this carbon, so no chiral center. Okay, now let's look at this. So we have one substituent ethyl, another is methyl, carboxylic group, and hydrogen. So this is the chiral center. Therefore, it will show 2 optical isomers, and the correct answer is D. Moving to reaction number 36. An SN2 reaction at an asymmetric carbon or compounds always gives an enantiomer of the substrate. No, because substrates and products have different configuration, and we know that inversion of configuration take place. Inversion. A product with opposite optical rotation, it is not necessary. May or may not. So product may have same optical rotation or may be different from the reactants. So this is also not possible. A mixture of diastereomers. This mixture of diastereomers is possible when there is one more chiral center. So if there is only one chiral center, then you will get the enantiomers only. So this is also not possible. A single stereoisomers, yes, and that in single stereoisomers is the inverted product, configuration. So the correct answer is D. The order of reactivity of the following alkyl halides for SN2 reaction. So order of reactivity depends on the stability of leaving group. Iodide is more stable as compared to bromide, or we can say that iodide is better leaving group as compared to bromide, and so on. Therefore, the order of reactivity will be alkyl iodide will be more reactive than alkyl bromide, and alkyl bromide more reactive than alkyl chloride, and so on. So the correct answer is D. Now, which of the following has highest nucleophilicity? So nucleophilicity depends on electron density and size of the nucleophile. If nucleophile is bulky, then its nucleophilicity will be lower. But here, if you see that size are comparable, so what we have to see, electron negativity of donor atom. So chlorine is more electronegative than oxygen, and oxygen is more electronegative than nitrogen, and nitrogen is more electronegative than carbon. Therefore, the carbon will have more tendency to give its electrons dense. So carbon will have highest nucleophilicity because it's so the correct answer is C. How many optically active stereoisomers are possible for butane 2,3 diol? So butane 2,3 diol structure is this one, and there are 2 chiral centers. So we can use this formula, 2 number of chiral centers. So 2 power 4. So 4 stereoisomers are possible, but the substituents are same. Therefore, in this case, the formula becomes 2 raised to power n minus 1. So therefore, answer will be 3. So it will have 3 optical isomers, and you can draw those 3 optical isomers. First will be this. Second, you can draw OH here, and this one second, and third will be its mirror image. So in reaction 40, the bond angle, it is asking the bond angle. So this has sp2 hybridized and it is sp3. So bond angle in sp3 case is around 109 degree and in case of sp2 is around 120. Therefore, the correct answer is A. Okay, this is all for today. Thank you very much for watching this video. Please like and share this video with your friends so that they can also get benefited. And next part of this video is coming soon. So take care. Bye bye.